Hello everyone, here's another Physics IB past paper review. This is from May 2018 and it's paper 2, question 5. Here we have an electron moving in a circular motion inside a uniform magnetic field. We're given the position here of the electron, and it's got a velocity that's going tangential to the circular motion, which means, of course, that we can talk about it having a speed. It's got a circular speed, so this would be the speed of the electron that's going to remain constant. And since the velocity is going to be continually changing direction, we can talk about the acceleration being to the center of the circle. This acceleration centripetal acceleration, which means it's going to have a centripetal force, and that force is coming about as a result of the magnetic field. So we get a statement that comes out about that we'll do in just a minute. Either way, this should all be familiar to you. We're given the velocity at this point P. So we're given the velocity of the electron as 6.8 times 10 to the 5 meters per second. And we're told the uniform magnetic field strength is 8.5 Tesla. So first up, we got to state the direction of the magnetic field. So it's at this point we start to invoke our hand rules. And of course, it's an electron, so we're going to be using our left hand rule. So let's put that on here. It's a negative charge, so we're going to be using our left hand rule. Okay, so here's a left hand. This one is using the thumb and the two fingers. I typically in class I'll use a flat hand because I like the idea of the palm of the hand pushing, and therefore it sort of gives this idea of a force. But we can use this as well. Some people prefer this hand rule as well. So just to change it up, we're going to go with this one. And so just to remind us, then the thumb is going to represent the motion of the electron. The fingers, or in this case just the single finger, this is going to be the magnetic field direction, and then the middle finger there is going to be the force. Okay, so we'll position our left hand rule in alignment with the P, this position of the electron, and then for 1 mark we just have to state the direction of the magnetic field. Okay, the other thing to remember is, of course, that when we're talking about magnetic fields in this regard, we're going to be, so this would be the force magnetic, we're going to be talking about Q velocity B, and we talk normally about it as perpendicular, or we could bring in our sine theta value as well, but normally we're interested in this perpendicular idea. So the magnetic field, because of the left-hand rule, the magnetic field should be perpendicular to the other two things, which is why we have all of these at right angles. Okay, so let's move our hand around and see if we can position it in such a way that it aligns with the velocity given and the force. Remembering that the force is going to be going to the center. It's going to be in here. This is going to be the force centripetal to the middle. And this is where I'm going to get you to move your hand around in this case, a pretty uncomfortable position. It's almost impossible for me to move this picture without inverting it in a kind of weird way. So just get your hand out, move it around, make sure your left thumb is pointing in this direction here. This is going to be your thumb here, and this force centripetal is going to be either your middle finger or your palm. So if you're using your palm, you're going to have to really bend your arm around. It's going to be in a funny, awkward position, but that will mean that your fingers, this part, will be the magnetic field, and that should be pointing up out of the page, which means the direction of the magnetic field is out of the page, which we would represent as just a dot, like that. Okay, so now in part B, for 1 mark, we're asked to calculate the the magnitude of the magnetic force acting on this electron in newtons. Well, this originates in a F net expression. So here we have the sum of all forces, and of course this is an accelerating system, so we would say this is ma. There's only one source of the force, and that's the magnetic force, and this acceleration is centripetal acceleration. So the ma centripetal ends up being the force centripetal, so this can become Fc. Of course, this is still Fm, and this is where we have our statement that you've probably got memorized, is that the force centripetal is the force magnetic, and then we can say V squared m over r, which you will recall from circular motion, is equal to q v b perpendicular. Well, the question is, which one do we need to find out? Well, we're trying to solve for either of these because they're both equal to each other. So let's have a look at what we have. We know the velocity of the electron. Well, actually, we also know that it's an electron. So we also know the charge. The charge is going to be 1 elementary charge. We would also know the mass. That would be 9.11 times 10 to the negative 31. Oops, put that in the wrong place. Oh well. And so what can we do? Well, the only thing we don't know is the radius. Okay, we don't know the radius. So let's ignore this part of the equation and solve for the force in QVB. That's really all we need to do. So let's put those in. We're going to go the force in this situation is going to be Q, which is 1.6 times 10 to the negative 19 coulombs, multiplied by the velocity, which is 6.8 times 10 to the 5 meters per second, and then the magnetic field strength is 8.5 teslas. So plug that into your calculator, and what do you get? Well, nice and easy, 9.2 times 10 to the negative 13 newtons. That's the force. Okay, so for part C, there's 3 marks here in part C, so most of the marks for this question are actually coming from this qualitative part where we have to explain why the electron moves in a certain way. So first up, why does the electron move at a constant speed? So recall that the electron, let's say it's here, it's moving instantaneously with a velocity that is horizontal to the page, but of course there's a force acting on it, which means that it's going to go in a circular path. And to get that motion, we are talking about a centripetal force, which would be perpendicular to the magnetic force. Remember, we did all the hard work in part B, where we made that statement that the force centripetal is equal to the force magnetic, but only if the magnetic field is perpendicular. So the force centripetal is perpendicular to the magnetic field. And that's kind of key, which means that the forces acting on the electron have zero impact on the direction of its velocity. In other words, let's see if I can do this nice and straight. This is the force. That's the force. Whereas this is its velocity. So if you think about this in terms of vectors, how much of this force is going in the horizontal direction? Well, 0. So if there's no force going in the direction of the motion, Newton's laws would say that the object is going to continue in its magnitude and direction until acted upon by an outside force. Well, as the electron moves, as it moves to the next position, let's say it's now here, its velocity is the same magnitude but a different direction, and the force is still going to act at a perpendicular 90 degree. So at no point in this electron's motion does the force have an effect in the direction of the velocity, and therefore it's going to have no effect on the magnitude of the velocity. It only has an effect on the direction. And that means the value, the constant speed, the magnitude is going to stay the same. So the force, we can say, therefore, the force acting on the electron only affects the direction because of this perpendicular nature. Okay? Part 2 is asking about why it moves in a circular path. Well, it moves in a circular path, again, the same reason, is because the velocity is at perpendicular to the magnetic field. And so this is where we get our statement that we did all the hard work earlier for when we made our F net expression. We said the F net's going to be an acceleration centripetal, and that's going to be equal to QVB. So we end up with this V squared M over R being equal to QVB, perpendicular. And so this is what causes this change in motion in a circular motion. And it's the same reason. It's because the force magnetic is the force centripetal, and this is the important bit, it's always perpendicular. Okay, now, in reality, you may have seen some bubble chamber stuff. In reality, as the electron moves through a medium, it would actually slow down. So don't get this confused with some of the particle track stuff you may have seen with particle physics. Normally what would happen is the electron would do this. And that's because it is slowing down. It is slowing down because the electron, as it moves through a medium, will interact. And some of the energy will be taken away from that electron in the way of reducing its kinetic energy. So therefore it will slow down. There are interactions. There would always be these little interactions as it's kind of colliding and interacting with the medium it's moving through. But one of the assumptions with this question was that there was no medium. It's in a vacuum. And in that case, we can ignore all of those interactions, or if you want to think about them as frictions. So there we have it. Question 5.